Hello everyone, today we'll be starting with Einstein's photoelectric equation. According to him, energy as quantum of radiation, or we call it as energy quantum of radiation. According to him, suppose this is a metal surface. According to him, when a photon of energy h nu, here h is Planck's constant and nu is the frequency. If a photon here Planck's constant h has a value 6.626 into 10 to the power minus 34 joules second. This is a constant term according to Max Planck, for his name. If a photon of energy h nu comes and strikes an electron, then this energy h nu gets divided into two parts, or gets split up into two parts. The first part is used up by the electron to overcome the surface barrier to come out. That energy we call it as work function. We write it as phi naught. Earlier I have written work function as phi. It must be phi naught. That is, we write it as h nu naught. And the second part of the energy is used to give this electron the velocity with which it will come out, and that velocity, with that we get the energy as maximum kinetic energy. Also we say V maxima. Kinetic energy formula is half of mv square. So this equation that is given by Einstein, we call it as Einstein's photoelectric equation. To sum up, the total energy that has been provided by the photon to the electron on striking on the top of the metal surface, E, that is equal to h nu, is equal to sum of the work function phi naught to overcome the surface barrier and to come out of the metal surface, plus the maximum kinetic energy that is provided to the electron. When you add these two energy, then you get these two energy work function, this energy and the energy at which the electrons will accelerate outside the metal surface. When you add them up, you get the energy of the photon. Or we can write it as h nu is equal to work function is h nu naught, and E dash, I am representing here the maximum kinetic energy, half of mv maxima, or maximum velocity of the electron square. This energy, if I transpose it, if I write like this, half of mv maxima square, then I can write it as h by taking common nu minus nu naught. And this kinetic energy maximum, if I represent like this k maxima, then I can write this h nu minus nu naught. This equation we call it as Einstein's photoelectric equation. Here nu indicates the frequency of incident radiation, nu naught indicates the threshold frequency, the minimum frequency at which the electrons will get ejected out, h is Planck's constant, and k maxima represents the maximum kinetic energy. Let's see the relation between stopping potential V naught we write, and threshold frequency mu naught. Then by using the Einstein's photoelectric equation, kinetic energy maxima is equal to h nu minus mu naught. This one you already know. This maximum kinetic energy, if you don't want to write half of mv square, you can even write like this. Potential is equal to work done per unit charge transferred. Now, potential, if you are talking in terms of stopping potential, work done in terms of energy, kinetic energy maxima, divided by charge or electron here. So if you write K maxima, we can write this E V naught as well in place of maximum kinetic energy. So if you write this as E V naught, then you get the relation frequency minus threshold frequency mu naught. This is the relation, or V naught we can write it as h nu minus mu naught divided by E. This will give us the relation between the threshold frequency mu naught and stopping potential V naught. We can write in terms of wavelength as well, or we can write it as V naught is equal to h by E. Nu is equal to speed of electron, it is nearly equal to the speed of light, c by lambda, wavelength, velocity by wavelength gives us the frequency, minus c by lambda naught. Like this also we can represent in terms of wavelength. So you need to know while solving the numericals. Now let us verify the laws of photoelectric effect, photoelectric emission, with the help of Einstein's photoelectric equation. Verification of photoelectric emission. By Einstein's photoelectric equation. Einstein's photoelectric equation is given by kinetic energy maximum is equal to h nu minus h nu naught, or h if you take common. This is your Einstein's photoelectric equation. This law or this equation successfully explains photoelectric emission these are as follows. Number one, if nu is less than nu naught, that is, if the incident frequency is less than threshold frequency, then what will happen? You can look at the equation. Nu is less than nu naught. If nu naught is bigger, then overall the value will become negative. That means you will have negative kinetic energy. Then kinetic energy maximum is negative, which is not possible. Therefore, the incident frequency should be higher than the threshold frequency. So we came to know that the incident frequency should be more than the threshold frequency. Then only the photoelectrons will get ejected out. Therefore, the incident frequency must be greater than the threshold frequency. Incident frequency must be greater than the threshold frequency for ejection of photoelectrons. This is the first point. Since one photon emits or ejects one electron, the number of photoelectrons is directly proportional to the intensity of the incident radiation. Third point, since kinetic energy maximum is directly proportional to the frequency of incident radiation, since or as h and nu naught are constants, therefore the kinetic energy of the emitted electrons is directly proportional to the frequency of the incident radiation. Or we can say that the kinetic energy of the emitted electrons depends directly on the frequency of the incident radiation. Depends on the frequency of the incident radiation. The fourth point, photoelectric emission is an elastic collision between a photon and an electron. Therefore, there should not be any time lag between the incident photon and the emitted photoelectron. Here, as I said earlier, on the surface of the table, if you keep one marble and with another marble, if you hit it hard with more energy, then this marble will bounce back. It will bounce and come out. So the collision between these two particles is elastic. In class 11 you studied when two particles moves in a straight line and they hit each other. After hitting it, they get separated. Then that type of collision we call it as elastic, in which kinetic energy is conserved. That type of collision we call it as elastic collision. And here in Einstein's photoelectric equation also we have seen the same way. When photon comes and strikes the metal surface, or on the metal surface, you know that free electrons are there. When it comes and strikes the free electron, then the electron gets ejected out. So these two, the photon and then the electron, they undergo elastic collision. And if there is elastic collision, then the moment it comes and strikes, that moment only the electron must get ejected. So time gap should not be there between the incident photon and the emitted photoelectron. This is how Einstein explained the laws of photoelectric emission. Here are some characteristic properties of photon. In interaction of radiation with matter, radiation behaves as particles called photons. So when radiation interacts with matter, then radiation behavior is exactly like particles, and those like particles we call them as photons. The second characteristic property, the rest mass, or we can say first the speed of photon is 3 into 10 to the power 8 meter per second. It travels at the speed of light, is equal to the speed of light. It is in vacuum. Then the third point, the property of photon is that it has zero rest mass. If a photon does not move, if it is at rest, then it does not have any mass. It has zero rest mass. Rest mass we indicate with m0. So like this, according to theory of relativity, the mass of a substance, mass when it is in motion, mass m is given by the rest mass divided by root over 1 minus v square by c c square. So with this, what you can get is m naught is equal to the inertial mass m multiplied by 1 minus v square by c square. Now we know that v, the velocity of photon or the speed of photon and the speed of light is almost the same. If both are equal, when v is equal to c, m naught will become 1 minus, if both are same, 1 will be 1 minus 1, 0 root over 0 will become 0, 0 into m will become 0, so m naught will become 0. So a photon does not have mass when it is at rest. When it moves, then only it will have mass, and that mass we call it as inertial mass m. Let us see the fourth point. The inertial mass of photon, mass is equal to energy divided by c squared, the speed of light square. It comes from Einstein's famous relation, E is equal to mc square. So mass is equal to energy divided by speed of light. Energy for photon is h nu divided by c square. So this will give us the inertial mass. Again, frequency, if you change it with wavelength, 1 by lambda, that also you can do. Then let us see the fifth one. Photon travels in straight line then the sixth point, energy of each photon is the same and is given by E is equal to h nu. H is Planck's constant and nu is the frequency. And from here you can get even energy of a photon is directly proportional to frequency because h is constant. Energy of a photon is directly proportional to the frequency of incident light. So energy of photon does not change when it travels from one medium to another medium. Point number 8. Wavelength of photon changes in different media therefore the velocity or the speed of photon is different in different media. different mediums, the speed of photon will be different. Point number 9, photons are electrically neutral. They are not deflected by electric and magnetic fields. Photons can show diffraction under suitable conditions. And lastly, one more point, as they undergo elastic collision, therefore kinetic energy and momentum is conserved, but the number of photons may not be conserved. So these are some of the characteristic properties of photons that you have to keep in mind. Thank you and have a nice day. In the next video, we'll continue with microwaves.